Welcome to lecture number 7 for ECE 320, Digital Electronics. Today we're talking about LEDs. Now, an LED is a light-emitting diode. What that means, pretty much, it's a diode. It allows current to only flow one direction. However, they're slightly different. These are diodes that convert current to light. In other words, the light it produces is proportional to current rather than voltage. They are extremely fast, capable of over 1,000, probably over a million flashes per second. And they're a simple way to output binary data, such as lights on, lights off. Now, if you go on eBay to a place like Lighthouse LED, kind of what I found is eBay is the place that you get the most current LEDs that are out there. So you can get your colored LEDs, RGB LEDs, high power LEDs. These are the Piranha LEDs. Those are like the scoreboards. We have RGB LED on a single package. Basically a pretty nice website. What I found is eBay has the LEDs about 2 years before the distributors like eBay have them. But anyway, if you go to Lighthouse LEDs, you can get, for example, an RGB LED. This is actually 4 LEDs in one package. The way it's built is you've got the red, green, blue LEDs, and it can either be common anode or common cathode. What I'm showing is the common cathode configuration. So it might be red, green, blue in a 4-pin package. To wire these up, if I get current through the LEDs, I get light. So if I connect this guy to 5 volts through a resistor, this one to 5 volts through a resistor, this to ground, I can turn on the LEDs, and depending upon the resistor, I can vary the brightness. So you can get these RGB LEDs for about $1.68. That's the 2020 price. The specs on them. The voltage across the LED is between 3.2 and 3.6 volts. Again, this is an LED or diode. Assuming an ideal diode model, the voltage drop is roughly constant as long as there's current flow. So this is the constant. It kind of varies depending upon the manufacturer, the color, the current flow, but it's in that ballpark. This is a current device. At 20 milliamps, it produces 10,000 millicandles. And a millicandle, well, one candle is the light output of a standard beeswax candle, kind of a non-scientific term. But actually, when candles fairly bright, splunkers use candles. You take a metal bucket, stick a candle in it, and then when you point the metal bucket around, that's kind of like a spotlight you can see in the cave. So you can see pretty clearly with just one candle. The LEDs on your board, they're also from Lighthouse LEDs. Those are 0805 LEDs that I think are about 100 millicandles for comparison. So this is, maybe 100 times brighter than the LEDs on your board. You can buy surface mount LEDs. The ones we use in ECE 376 are the 0805 green LEDs from Lighthouse LEDs. They're about, again, 3 to 3.2 volt drop across them, 500 millicandles at 20 milliamps, and the wavelength is green. That's the scientific term for color, 521 to 527 nanometer wavelength. You can get more powerful LEDs. Search eBay for like a 100-watt LED, and this is one site that came up when I tried it. This is an LED. Again, you have the anode right here, the plus side. Here's the cathode, the minus side. And this puppy, when you power it, gets insanely bright. This LED takes between 28 and 36 volt drops across it. That's this voltage drop. And 3 amps. Multiplying it all out, it's about a 100-watt LED. Produces between 9,000 and 10,000 lumens. A 100-watt light bulb is about 1,000 lumens, so this is like a 1,000-watt light bulb equivalent, insanely bright, for only $2.76 without the driver. With the driver, it's $14. You can also buy diodes that are laser transmitters. If you search eBay for Arduino laser diode, Arduino is kind of a buzzword used on eBay, meaning stuff for hobbyists to use, like we would use in our class. This is an example of them. They're about 42 cents each. This is 10 for $4. Again, this is an LED. To power it, you need 5 volts, a resistor, and the other pin going to ground. Which one I'm not sure, but that's kind of how you power it. This will output a laser beam, and with that you can measure how high you jump. Put a light sensor over here, and if I'm breaking the laser beam, I can know I'm on the ground. When I jump in the air, the laser beam hits the photo resistor. Ooh, we have a guest appearance by Momo. Say hi to Momo. Or you can also do on-off keying and output binary data. I could do amplitude modulation, whatever you want to do with the diode. So those are some of the options with diodes. Now the characteristics of an LED are just like any old diode. It's exponential in nature. The way it's specified is to specify this curve. They specify what the voltage is at a specific current, like 2.4 volts at 50 milliamps. It's actually going to vary as the current varies. If you use an ideal diode model, that means that the voltage is fixed. It's 2.4 volts as long as the current's positive. And again, that's not entirely accurate, but usually it's good enough for modeling. The way diodes are specified is they'll typically tell you the name of the diode, like these are the RGB LEDs. There should be one in your lab kit. The wavelengths for the red, green, blue. The max current you can supply through the diode. The brightness based upon current. Again, this is a current device. If you have the current, you have the brightness. And the voltage drop. That's for your ideal diode model. And purchasing cares about price, so it also tells you the price. That's typically how diodes are specified. The other diodes, like the red, green, yellow. Red isn't a scientific term. The wavelength of light actually tells you, it's a more scientific way of describing it. So this is primarily, or the highest energy is at 625 nanometers, and there's a little bit of variation in it. Like everything, it's a bell-shaped curve, centered at 625 nanometers, and it's actually fairly narrow. It's usually like plus or minus 5 nanometers. 625 nanometers is red, 592 is yellow, I think blue is 470, purple is 400. The brightness is also specified for them. Here, this is in lumens. This is in millicandles. That's one of the annoying things about light. There's different ways of defining it. Low light levels are defined in millicandles. Higher are in lumens. We'll talk about that a little bit later. And for an ideal diode model, you need to know what the voltage drop is. So this is the ideal voltage drop at 20 milliamps, the voltage drop at 120 milliamps. Again, this is a diode, so as long as the current's positive, the voltage will be pretty close to 2.15 volts, or whatever these are. So with that, if I have a circuit with an LED, I can calculate the current and the brightness. So for example, suppose I took a surface mount LED that's 180 millicandles at 20 milliamps, 2 volt drop at 20 milliamps. Find the current and the brightness for this circuit. Well, using an ideal diode model, if this is 2 volts at 20 milliamps, it's 2 volts at any current. So that's roughly 2 volts right here. I now have 3 volts going across this resistor. 3 volts at 22.2 kilo ohms is 1.36 milliamps, so that's ID. And I can now find the brightness. 20 milliamps is 180 millicandles. It's this percentage of 20, that percentage of 180 millicandles, 12.27 millicandles. And as I vary the resistance, I vary the current. The resistor sets the current, sets the brightness of the LED. Second example. Suppose I have a 3-watt white LED. With these specs, it drops 3.4 volts at 750 milliamps. Multiplied together, you get about 3 watts. And outputs 200 lumens at 750 milliamps. Design a circuit to drive it at 500 milliamps. Well, again, using an ideal diode model, if this is 3.4 volts at 750 milliamps, it's also 3.4 volts at 500 milliamps. Again, for an ideal diode, it looks like this. Here's the spec, 750 milliamps. Come down here to 500 milliamps. The voltage is still the same, 3.4 volts. To set the current, if I want this to be 500 milliamps, I have 12 minus 3.4, that's the voltage drop, at 500 milliamps, gives you 17.2 ohms. And that's my design. The brightness is going to be proportional. 750 milliamps is 200 lumens, is this percentage of full current, that percentage of full brightness, 133 lumens. Third example. Let's take one of those Piranha LEDs, the RGB LEDs that are used in scoreboards. Come up with a circuit to make it produce purple light. So like if you're a Vikings fan. So if I want 6900 millicandles red, green, blue, and kind of where that comes from, if you go to colorwheel.com, this is kind of a nice website, or this is actually rapidtables.com. This linked on Bison Academy. As I move around, I can sit there and see the different colors. Right here is the red, green, blue. 255 is full brightness. 0 is no brightness. So for purple, kind of here. Try to get the color purple that you want. Once you pick it, this says the red, green, blue. That percentage is 250, 255. Let's see where we're at. So if I want this much color, red, green, blue, then 20 milliamps is 10,000 millicandles. For 6,900 millicandles, I want 13.8 milliamps in red. The resistance that I need is the red LED has got a 1.8 volt drop across it. So the remaining voltage is across the resistor. The remaining voltage at 13.8 milliamps gives you 594 ohms. For the green LED, to produce 3,100 millicandles, I need this percentage of full current, 6.2 milliamps. The voltage drop across the green LED is 3 volts, so 10 minus 3 over 6.2 milliamps is 1129 ohms. Make that 1129. Likewise for blue, for 6,800 millicandles, I want the current to be 13.6 milliamps, and the resistance that does that is 514 ohms. So by varying the resistance, I can vary the color. So here's kind of a handout. Let's let you spend a couple minutes to work on this one. Come up with the resistances, or assume all resistances are 1K. Determine how bright each LED is. Okay. So to do that, if all these are 1K, the red LED's got 1.9 volts right here. The voltage drop across the resistor is 8.1 volts. 8.1 volts at 1K is 8.1 milliamps. There's spelled milliamps there. And the brightness then is proportional. It's this percentage that full current, rate of current is 20 milliamps. It'll be that percentage of 10,000 millicandles. Which works out to, pulling up my favorite calculator. Let's see, 8.1 milliamps divided by 20 milliamps times 10,000 millicandles. This is 4050 millicandles. Likewise for green, likewise for blue. The second one, find the resistors so that the green LED is outputting 3,000 millicandles. And again, what I would do is I need to first find the current. The rated current is 10,000, so it's this percentage of rated current. Rated current is 20 milliamps. So I need 3/10 of 20 milliamps. I need 6 milliamps flowing. The voltage drop for a green LED was 3 volts. So this right here is 3 volts. I've got 7 volts at 6 milliamps. So 7 divided by 0.006. 1166 ohms. Okay, so that's kind of how you draw LEDs. And by varying the resistances, you can get pretty much whatever color you want. That's primates. Primates see 3 colors, red, green, blue. Mix those 3 colors together, and you can produce whatever color you want. Other animals see different colors. Dogs see 2 colors. Birds see 4 colors. We're primates, so we just have 3 colors. Other things you can do. You can build insanely bright lights. For example, if you go to this website, they built a 1,000 watt
homemade LED flashlight. It's commonly accepted that LEDs put out about 7 times more light per watt than halogen bulbs. With that being said, a halogen equivalent would draw 7,000 watts. That's a lot of power, and a lot of light. My build consists of 10 100-watt LED chips in a row. Each one is attached to a large heatsink with bolts and thermal grease to help the heat transfer. Every chip has its own driver, which is just attached to the heatsink with wire. These drivers take the 12 volts from the battery and bump it up to about 35 volts for the LED. I drilled holes in all the heat sinks and mounted aluminum bars on each side to hold the array together. This also acts as a handle. Each LED has its own glass lens to make the beam width roughly 60 degrees. I attached some bent aluminum bars to hold 2 8 amp hour 3S LiPo batteries running in parallel. This gives the light about 10 minutes of runtime. I was back to the headlight. And back to the headlights. Up next is a series of photographs shot on a stormy night with low cloud cover. This is without the LED, and this is with the LED. You can see how it lights up the clouds. The camera exposure settings did not change.
Okay, so it's kind of a fun video showing what you can do with a 1,000 watt LED, basically light up the side of a mountain. A couple side lights for powering LEDs. If you have a couple LEDs that you want to power, there's a couple ways that work. One way that doesn't work. You can put the LEDs in series. If each of these has, say, a 3 volt drop, I now have a 12 volt drop across all 4 of them. That works. I can put the LEDs in parallel if I use a separate resistor for each one. What doesn't work is putting them in parallel without the resistor. The reason being is the voltage drop for the LEDs won't be exactly the same. So suppose this one is 3 volts, this is 3.1, 3.2, 3.3 volts, the voltage drop across it. What happens is the smallest one wins. All the current, or almost all the current, will go through this LED and it'll burn out. Once it burns out, the next lowest wins. This takes almost all the current, it burns out, then the next. This is how you burn out all your LEDs. You need separate resistors for each LED in parallel. You can buy LED drivers. Now, one way to vary the brightness is to vary the resistance like we did before. Another way is to use pulse width modulation. So if I design the circuit so the LED is at full power, say 20 milliamps for the previous one, and I could build a circuit that does this. If this is only on for 1/4 of the time, the light is flashing, but for us it looks like it's 25% brightness. If the on time is half, it looks like it's 50% brightness, and so on. So by varying the pulse width, I can make the LED look like it's getting brighter and dimmer. It's actually flashing. This is a 555 timer, something we'll talk about a little bit later. The way the 555 timer works is I charge for the on time and discharge for the off time. If this resistor is way over here, it charges very quickly, then slowly discharges. That'll give you a very low duty cycle. If I move the potentiometer over here, I charge quickly, and I charge slowly, higher resistance, discharge quickly. That gives you a longer on time. So by varying this potentiometer, I can vary the pulse width at this point. This is a transistor switch that we'll talk about a little bit later in this semester. This is an electronic version of a switch that turns on and off. When I have 5 volts at the output, the switch turns on, I have current flow. When I have 0 volts, the switch turns off and the LEDs turn off. So this is another way to build an LED driver where I can vary the brightness just with a 555 timer. Now, one question you might wonder is how efficient are LEDs? Well, that's actually a really hard question to answer. It depends upon how you define the word 100%. The human eye is sensitive to different colors of light, and the sensitivity varies with the color. For example, this comes from Wikipedia. This is the wavelength. This is violet, blue, green, yellow, red. The highest sensitivity is to green light. So if I have a light that's just green, then I can get 683 lumens per watt at 100% efficiency. If instead of green light I have white light, it really depends upon what you mean by white. How much energy is at each frequency? So, kind of arbitrary here, define an ideal black body where it's band limited between 400 and 700 nanometers, radiating at 5800 degrees Kelvin. If I give it that definition, then 215 lumens is 1 watt. Again, it really depends upon what you mean by the word white. So let's go with this one. Define 100% efficiency to be 215 lumens per watt. Well, if you go to Amazon or other websites like that, I can find different types of light bulbs. The incandescent light bulb from 2000 produced about 5.27 lumens per watt. That's a whopping 2% efficient. This is one of the reasons incandescent light bulbs are banned in Europe. They tried to ban them in the United States, but our former president complained that his skin looked better under incandescent lights rather than LED lights. Plus, people will sell them as a 98% efficient heater that also produces light, and heaters aren't banned. So it's kind of hard to ban anything in this country. They are insanely inefficient. You can get better incandescent light bulbs. GE came out with a more efficient version that's 5% efficient. Again, still not very good. Halogen bulbs are a hair more efficient. Back in the 90s and 2000s, people were using CFL, compact fluorescent light bulbs. These are much better. They are 26% efficient. Over the last decade, people have been switching over to LED lights. LED lights are, like this one, currently 37% efficient. In theory, they can get to 80% efficient. So this is one of the reasons there's a push towards LED lighting. They are 10 to 20 times more efficient than the incandescent light bulbs. They are so efficient that if you bought an LED light bulb, it'll pay for itself in just a couple months, just from the electricity savings. You might have also noticed that street lights are changing color. 30, 40 years ago, street lights were incandescent light bulbs, 2% efficient. That's a problem for a city. If you look at a city like Fargo, Fargo spends a lot of money on lighting. If I can reduce the amount of money, use more efficient light bulbs to reduce the electricity demand, the city can save quite a bit of money. Well, back in the 1990s, 2000s, they switched over to mercury lights. Those are kind of the white lights with a kind of a bluish halo around them. They are better than incandescent, 14% efficient. Around 2000, 1990 to 2000, the lights turned orange. That's when they switched to the sodium vapor lights. Those would be kind of the yellowish orange lights. These are much better, 34% efficient. Now the street lights are turning into LED lights. That's because they are more efficient. They're about 36% efficient. And they are getting better. In theory, an LED light could be 80% efficient. We're not there yet, but getting there. So that's the efficiency of light bulbs. That has some fairly significant implications. Back in the 1990s, about 20% of the electricity produced in the US just went to lighting. By switching over to mercury vapor, incandescent, LED lighting, things like that, now it's pretty much LED lighting. We're now only using 5% of the energy we produce towards lighting. That 15% reduction in the energy use means that's fewer coal plants that we need, less coal that needs to be burned to produce that electricity. We need fewer power plants. The older, less efficient power plants can be retired, and brownouts and blackouts can be avoided because we're just not using as much energy. That's part of the reason why the incandescent light bulbs, those 2% efficient light bulbs, are banned in Europe. You can still buy them in the US. In fact, they are so inefficient, there used to be a thing called the Barbie Easy Bake Oven. It's a 25-watt light bulb in a metal box. You put it in there. Well, it's basically an 98% efficient heater, 2% efficient light bulb. Put it in the metal box. You can make cupcakes, brownies, things like that. LED lights are way, way, way better. So that's one of the good things about being in electrical computer engineering, is if you care about the environment, you want to produce less CO2 gas. One way to do that is to switch over to LED lights, which is us, electrical engineers. So anyway, that's lecture number 7 for ECE 320, LEDs.